The code snippet below serves to guide you in setting up the Vantage library through pip, pulling in vital libraries like NumPy, PyTorch, and Matplotlib, and establishing a framework for handling financial time series data in deep learning models. Delving deeper into the code 1. The Vantage Python package is installed to facilitate seamless access to stock market data. 2. NumPy supports numerical computations, PyTorch aids in constructing deep learning models, and Matplotlib is employed for generating visualizations. 3. Essential deep learning components are arranged, encompassing neural network layers, optimizers, datasets, and data loaders. 4. By importing the time series class from the Vantage library, the code retrieves historical financial data effortlessly. 5. A confirmation message signaling the successful loading of all libraries concludes the execution. This code snippet is an invaluable resource for individuals keen on delving into financial time series data processing and constructing predictive models employing deep learning methodologies. Leveraging Vantage broadens access to financial market data, whereas NumPy, PyTorch, and Matplotlib streamline data manipulation, model development, and data visualization, respectively. Contained within this script is a Python dictionary serving as the repository for setting configurations pertinent to a project focusing on financial data analysis and forecasting. Let's delve into the breakdown of each segment in this configuration dictionary. 1. Vantage. This section houses settings associated with the Vantage API, encompassing details like the API key, stock symbol, data output size, and the access key for adjusted close prices. 2. The data. Here you'll find specifications pertaining to the dataset, including the window size utilized for feature engineering and the proportion for segmenting the dataset into training and validation subsets. 3. The plots. This segment configures settings for showcasing plots, ranging from toggling plot visibility to setting axis tick intervals and assigning colors for actual data, training data, validation data, and predicted data in the plots. 4. Model. This part lays out the parameters for the LSTM neural network model, outlining the input size, quantity of LSTM layers, LSTM unit size, and dropout rate aimed at curbing overfitting. 5. The training. Steering various elements of the training procedure. This section dictates the device to employ PU or UDA for GPU, batch size, epoch count, learning rate, and the increment size for the learning rate scheduler. Such a configuration dictionary proves pivotal in upholding uniformity across assorted sections of the codebase while streamlining the process of adjusting configuration sans direct alterations to the source code. With a setup like this in place, experimenting with diverse parameters, datasets, and models turns into a more straightforward endeavor, minus the need for direct tweaks to the code. The code presented here establishes a function named downloadData, responsible for fetching daily stock market data of a specified symbol via the Vantage APIs. By leveraging the predefined configuration settings, the function securely accesses the API, retrieves the data, and, if desired, crafts a visual representation. To break it down, 1. It first imports essential libraries like time series to interact with the Vantage API and various plotting tools. 2. The function then reaches out to the Vantage API to procure daily adjusted data for a designated stock symbol, capturing both the data itself and accompanying metadata. 3. Subsequently, it handles the data by isolating dates and closing prices, reordering them to suit plotting requirements, and computes the data point count and date span. 4. If prompted with the plot flag is true, a graphical representation is formulated, exhibiting the daily closing prices alongside tailored axis markings and grid lines. 5. Finally, the function furnishes the extracted data encompassing dates, closing prices, data point quantity, and the range of dates shown. This functionality is key for obtaining and illustrating daily stock market insights based on user-specified settings, thereby facilitating trend analysis and decision-making. By encapsulating the data retrieval and processing stages, this function enhances code structure, flexibility, and readability, advancing overall code quality. In this code, there is a class called normalizer, designed for data normalization and inverse transformation. The fit transform function computes the mean, mu, and standard deviation st of the given data across a specific axis 0, and then proceeds to normalize the data based on these computed values, delivering the normalized data as output. For the inverse transformation, the inverse transform method accepts normalized data and utilizes the previously determined mean and standard deviation to revert the normalization process, restoring the data to its original form. Data normalization, a widely adopted data preparation procedure in both machine learning and data analysis, serves to adjust numerical data to a standard range. This step holds significance as numerous machine learning algorithms exhibit enhanced performance or quicker convergence when input features share a similar scale. The normalizer class serves as a beneficial and reusable solution for normalizing and inversely transforming data efficiently for modeling tasks. The provided code snippet introduces functions geared towards data preparation for a machine learning model. This includes the prepare.datax function, which generates input data.datax through a sliding window technique applied to normalized close-price data. By segmenting the data into subsets determined by a specified window size, it lays the foundation for subsequent analysis. On the other hand, the prepare.datax function creates output data.datax by shifting the input data by the window size. Furthermore, the prepare.data function amalgamates the aforementioned data preparation operations. It divides the input and output data into training and validation sets using a designated split size. In case the plot parameter is activated, a visual representation of the training and validation data is generated. This code plays a pivotal role in the machine learning workflow as it orchestrates data structuring conducive to model training and performance assessment. By guaranteeing the correct alignment of input and output data for the machine learning algorithm to discern patterns and offer projections, it sets the stage for informed decision-making. Additionally, the visualization component enriches the comprehension of data distribution and trends, which are instrumental in scrutinizing and interpreting model performance. The code provided here presents a custom dataset class named time series dataset, which is a subclass of the dataset class. Its main objective is to format time series data to be compatible with training neural networks, particularly those utilizing LSTM short-term memory architecture. Within the GNet function, the input data X undergoes reshaping through NIP to expand DIMS to introduce an additional dimension, thus reshaping it to batch sequence features as required by LSTM models. Subsequently, both X and Y are transformed into NumPy arrays with a data type of NIP. Float32. The len function retrieves the dataset's length corresponding to the X data size. Through the digititem function, individual samples from the dataset can be accessed using an index edx, providing a tuple of edx. Subsequently, two instances of the time series dataset class are instantiated for training data dataset train and validation data dataset vol. Following this, the shapes of the input features and labels for both datasets are displayed to confirm their accuracy. This snippet of code proves vital as it preprocesses time series data into a format suitable for LSTM models, ensuring proper shaping and data types are in place prior to model training. By encapsulating the data preparation logic within this customized dataset class, it enhances code reusability and maintainability for future projects involving similar time series data. In this snippet, we delve into crafting a bespoke LSTM model class as an extension of PyTorch's NIN module. Let's delve into the details to kick things off. The LSTM model class emerges, equipped with pivotal parameters like input size, hidden layer dimensions, the count of LSTM layers, output dimensions, and a dash of dropout rate. Moving on to the constructor designated within the class, its prime mission encompasses setting the stage with the hidden layer capacity, outlining the linear layers realm, and kindling the ReLU activation function, sculpting the LSTM layer silhouette, infusing a smidgen of dropout essence, and masterminding the closing linear layer that unearths the output. As a final touch, an invocation to the init weights is made, ushering in the weight inception ritual for the LSTM module. The initiation ceremony of init weights takes the reins in kickstarting the LSTM module's weight genesis, steering diverse routes for bias, input hidden weights, and hidden weights. In the realm of the forward function, we sketch the roadmap for the model's forward drive. It orchestrates a symphony of linear metamorphosis and activation charm upon the input tensor X, ventures forth through the LSTM labyrinth, harnessing the troves of hidden state output. It deftly reshapes the subtle whispers of the hidden states, adorning them with a sprinkle of dropout air, ushering them through the ultimate linear portal for prophetic revelations. Wrapping up, a bespoke vessel of LSTM model is forged, entwined with the essence of configuration parameters. The model is then entrusted to the tender care of the designated device for enactment. Whether it be the steadfast P or the nimble GPU, this craft is harnessed to mold a distinctive LSTM entity within PyTorch. Be it for prophesying time series trends or deciphering sequential puzzles that hinge on the prowess to apprehend long-lasting entanglements. This tailored touch empowers us to etch the architecture and conduct of the model to mirror the bespoke demands of the enigma at hand. The provided code excerpt outlines the procedure for training a neural network model with PyTorch, offering a comprehensive breakdown of its functionality to commence. The runs epoch subroutine conducts a singular training or validation epoch on the designated data coder. It systematically processes each batch within the data loader, executing a forward pass to procure predictions via the model, computes the loss, and modifies the model parameters if it signifies a training epoch. Within the runs epoch function, the model's status transitions to training mode model. Train when is training holds a true value. Conversely, it shifts to evaluation mode model. Otherwise, this adjustment influences the dynamics of certain layers such as dropout and batch normalization during the training and validation phases. The optimizer assumes the role of updating the model parameters in accordance with the loss computed during each epoch iteration. When his training evaluates to true, the gradients are computed, subsequently allowing the optimizer to adjust the model parameters employing loss. Backward in optimizer step. The learning rate lore undergoes modifications via a scheduler following each epoch. Contingent on the specified step size and gamma values, both the training and validation data coders are instantiated applying the data loader class, furnishing an iterable structure over the dataset. The loss function referred to as criterion, optimizer specifically the atom optimizer, and the learning rate scheduler step lore are all configured with specified parameters. The training loop executes for the predetermined number of epochs num epoch. In each epoch, runs epoch is invoked for the training and validation data coders, facilitating the estimation and display of the training and validation losses. Alongside updating the learning rate with the scheduler, this code segment is crucial for automating the neural network model training process, delivering an organized and effective pathway to execute training and validation epochs, alter model parameters, and manage learning rate adjustments. This structured approach underpins optimal learning for the model, promoting adept generalization capabilities on unseen data. This snippet forms a crucial component of a stock price prediction machine learning pipeline. Let's delve deeper into its functionalities. Firstly, the code readies data loaders to handle the training and validation datasets in manageable batches specified by the batch size setting. Next, it switches the model to evaluation mode via model eval, adjusting the behavior of certain layers for consistent results, especially during inference tasks. Subsequently, it loops through the training and validation data loaders, leveraging the trained model to make forecasts on each data batch, storing these predictions in NumPy arrays. Following that, it assesses the configuration to decide if plotting is necessary. If enabled, it crafts and showcases two plots. The initial plot juxtaposes real prices against predicted prices for both training and validation sets. The subsequent plot zooms in on predicted prices for the validation set to scrutinize them in detail. Moreover, the code tailors the plot styles with diverse configurations like colors, labels, and ticks to enhance the visual's informativeness and appeal. This code holds pivotal importance in visually assessing the model's performance on training and validation sets. It aids analysts and stakeholders in gauging the model's stock price prediction accuracy and spotting any trends or inconsistencies between predicted and actual values. Ultimately, these visual representations play a key role in informed decision-making concerning the model's reliability and the necessity for potential adjustments. This specific code excerpt handles the task of visually showcasing the forecasted stock price for the upcoming trading day using a machine learning model. Here's a breakdown of its functionality. Firstly, the model gets activated for evaluation by employing model eval. Next, the undisclosed input data on scene undergoes preprocessing to conform to the model's required format. Subsequently, the model predicts using the preprocessed input. The prediction is then transformed back into a NumPy array and subjected to inverse transformation employing a sailor. The last predicted value is singled out and rounded to enhance its presentation. If on plots evaluates to true, a plot is generated to display the real prices, the historical predicted prices, and the projected price for the upcoming trading day. Preparation for plotting involves selecting specific ranges of data points and introducing markers for annotations. Data adjustments for plotting purposes include replacing zeros with none. The plot is composed of 3 lines: actual prices, predicted prices for previous days, and the predicted price for the next trading day. Title, legend, and grid configurations are set for the plot. This code proves beneficial for visually grasping the performance of a machine learning model in predicting stock prices. Visualization aids in interpreting the model's efficacy and assists in making judicious decisions grounded on the forecasts. It delivers a comprehensive snapshot of the anticipated stock price patterns, thereby aiding in affirming the model's effectiveness.